Yeah.
The fork function we talked about yesterday.
The fork?
Yeah.
Yeah.
Is basically like copy um, bring out twice of one program.
Mm-hmm.
I try out 0 to 10, and then the fork function is going to bring again, bring down again.
You did it 10 times?
No, twice.
Twice.
Yeah.
Okay.
Basically, just like copy.
Yeah. So fork is kind of quirky. So here's your main program, and you say fork,
Yep.
and your main program continues, but it creates a fork, right? And these are basically running exactly the same code.
Yeah,
So if you say fork on both of these, right, this will create a new branch, and this will create a new branch, and now you got 4 threads. Right, so every time you fork, you kind of double. But usually that's not what's happening, because usually what we're going to do is we're going to do something different here from here, right? We don't normally just want 2 copies of our process running. We want 2 processes that are doing 2 different things. So the difference is when you fork, you create a new process, right? So let's do it like this. Here's our main process. Here's your call to fork. So if you're the child process, the return from fork was 0. If you're the parent process, the return from fork is the process ID of the child. And that's the only difference between the processes. So if we call fork and we save the status, bless you. Alright, so if the fork returns 0, we know that this is the child process. If it returns something non-zero, it's the parent process. And let's go ahead and print out the fork's return. Alright, so main thread came once, and then we forked, and so there was a child and a parent. And so let's do something in here. Let's just execute a PS command using good old system. That's a little sketchier than I expected. So let's do a PS-L. All right, so we've got 2 PSs, and it looks like they're interleaved, right? So we got the header from each of them, and then we got the first line from each of them, and so on and so forth. So that's a little strange, but not entirely unusual. So ignore every other line. So this is our original bash shell. This is the fork1 process that we started from bash because the parent ID is 943, that's bash. This is the cloned fork process because its parent ID is 981, which was that original command that we ran, right? So this one is the child, this one was the parent. And then each one of those fires off an instance of shell, and each one of those fires off an instance of PS. And you can trace it through. So 981 is the parent of this process. 983 was the shell, and 983 was the parent of this call to PS. And the parent told us the return from fork was 31982. That's the process ID of this second instance of fork1. So, what is this useful for? Because like I say, we don't normally just want 2 copies or 3 copies of your program running doing exactly the same thing.
Are these programs running on the same chip, same processor?
Same processor, but I've got 4 cores in here, so they're probably actually executing simultaneously, at least to some degree.
So it automatically multi-threads if it can?
Yeah, which
That
is
makes
kind of
it
nice.
useful.
I believe. Let's double check that. I know with Java it does, and when we do this stuff in Java, it will be night and day. It'll be like really cool.
Do you know if it works the same way in Windows?
I don't know. Let's do some test code and see what it does on Linux. So I'm going to run this in the background, and I'm going to use the top command. And yeah, so we've got 2 processes taking about 100% of the CPU, so those are running on separate cores. And then this is probably my interactive process. So that's good because I need to do something with that later this week. So that was a good test.
So you could fork it and have one of them processing input and the other one taking the input?
Yeah, so this is a classic reason why we want threads. Suppose, hypothetically, you're taking a course like CSE 223, and suppose hypothetically you've got a programming assignment to write a chat program, where you can connect 2 computers over a network, and first person can type, and what they type appears on the other person's screen, and the other person can type, and it appears on the first person's screen, right? And if you were to do this in C, right, your first user would do something like, you know, read a bunch of characters from the keyboard, and then, so let's put this into, you know, some character buffer, and then send buffer to user 2, and user 2 is doing the same thing. So read a buffer from the user and then send the buffer to user 1. So that's one direction of transmission, typing over here and it's getting sent to the other user. This person's typing and it's getting sent to the first user. But you also want to be doing something else. You want to be reading stuff that's been sent from user 2 and then print that stuff. And over here, you want to read stuff from user 1, and you want to print that stuff. Well, we want to do this repeatedly, right? So the problem is, if I make a loop like this, I can type something, hit enter, it goes to user 2, and then it's going to wait for user 2 to send something to me, print it out, and then it's going to go back and wait for me to type something. And you're forcing the two processes to kind of move in lockstep, right? I can send something, and I can't send something else until I receive something from the user. And over here, they can send something to user 1, and then they wait here until they get something from user 1, print it out, and then go back. And what we really want is a pair of loops. We want a loop which continually waits for you to hit enter and sends whatever you type to user 2, waits for you to type, sends to user 2, and so on. But at the same time, we want to be reading stuff from the user 2 and displaying it, right? That's two processes. And if you don't break this into two processes, there's no real easy way to do this. Because this fgets is what we call a blocking read. When you say read 120 characters from standard in, nothing happens until the person hits enter, right? They can sit there, they can go off and get coffee, they can come back, they can hit a few characters, they can do some backspaces. Nothing happens. You're sitting inside this call to fgets until they hit enter, which means all of our other code is not executing, right? So typically when you write a program like this, early on you create another process, and that process is doing this part, this looping, and your main process might be doing this looping. So that's kind of a classic reason why we want to be able to make threads. And that's an assignment in 223. That'll be one of our last assignments, is a chat program. And so we'll be doing multi-threaded programming with that. Other possibilities, you're writing an editor and you want to auto-save every 30 seconds. Whatever the person's typed, you want to write it out to a temporary file so that if something goes wrong, you have a recent copy of their work, right? And writing their file to the disk might take 5 seconds, right? So how annoying is it if while you're typing in your document every half minute, everything freezes for 5 seconds while it writes to the disk, right? It's really annoying. Yeah. So you create a new process, and the whole purpose of that process is to take a snapshot of what you've written so far, send it off to disk. And when it's done, then that process just exits silently. And so it's happening in the background. So this is sneaking up to sort of the ultimate reason why we want to have forks and multiple processes, which is to have an operating system, right? We want multiple things happening at the same time. There's a process running in the background that's updating my clock, right? There's a process running in the background that's monitoring the internet and will let me know when the connection dies. There's a process looking for Bluetooth connections. There's Kazam recording the desktop, and so on and so forth. We typically have, a few hundred processes running in our operating system at all times. And those processes, in this case, were all created by call to fork. So if we go back to the beginning and we do a PS of every process on the system, process ID 1 is something called a init. Okay, that's the creator of most other processes. It's actually kthread-d. But basically when you boot up your system, there's a program running. Okay, and how that program starts running is a whole topic in itself. But ultimately there's a program running, and that's the only thing that's running, right? It's just a bunch of instructions executing. It's like when you boot up an Arduino processor. How many people here play with Arduinos? Oh, come on.
I played with the Pi.
Okay, Pi is cool. Play with some Arduinos if you haven't. Little standalone, programmable in C or something like C, and you can interface with the outside world. And they're like $10 at Amazon, and you can do anything with them. But it's a single program that's executing when you put power on these things. So you load a program into your Arduino and it remembers what the program is, and then the next time you plug it in, the program starts running, right? So that's kind of what happens when you boot up a machine. You have one process running, but that process ultimately starts making forks. And each time it forks, those child processes become these other processes that are doing things like whatever these things do. I don't even know anymore. Watchdogs are looking for things like, power dropout or inactivity or things like that. But these are the things that that make your system work. Let me hop onto the server. All right, so my bash process is 32356. So I'm going to do ps-elf, which shows me all the processes on the system. I'm going to search for 32356 using grep. And I get the following lines. I get this line, which is bogus, because I grepped for 32356, so that showed up there. But here's my bash shell. Let me make this a little smaller. Right, so here's my process, 32356. That's bash. Its parent process is 32355. So we can search for 32355. And that is this process, which is something called SSHD, and it was run with arguments of Nick at PTS/1. And that parent's process ID is 32346. And so we can look for that process. And 32346 is another SSHD, but it's got an argument of Nick and it says privileged. And that process parent's ID is 53538. And 53538 is this process called user/sbin/sshd-d, and its parent's process is ID1, which is a NIT. So we've got a family tree here. And I'll switch over after I write this. So 538 was the parent of my SSHD. And that's the parent of this. Alright, so we've got a process map here. A NIT is that first process that's created when you boot, and it created a process called SSHD, which in turn created a process called SSHD, but with different arguments, which in turn created another process which was also SSHD, but with different arguments, which in turn created a process called bash, which in turn created a process that was executing PS when we started all of this a few minutes ago.
That's a lot of processes.
That's a lot of processes. That's why there's 200 some processes running on a system, even when it looks like you're not doing anything. So, SSHD. So how many people here have used SSH? So this is what I keep using when I want to connect to the server. I do SSH nick at whatever machine I'm trying to connect to. And normally it asks you for a password. I've got it set up so it automatically authenticates. But it's a secure way to make a connection to a remote machine without having to send the password in plain text. Old school connections used a program called Telnet, and they would say username, and you type your username, it would say password, you type your password, and it would just go out as plain characters over the network. And particularly with wireless, right, you just need a receiver, and you could grab people's information. So SSH is the secure version of that. But what's happening when I run this SSH command, I'm typing that command on my laptop, right? And somehow I'm connecting to this machine sitting probably somewhere in California that we call linuxengrcs.com. And now everything that I type on my laptop is being sent to that machine, and the machine is sending some response, and I'm seeing it on my screen. So this SSH is just a program. Right, so it's just a program in user bin. It's probably written in C. But this SSHD is what we call a daemon. And I don't know why it's called a daemon, because everyone calls it a daemon. There's an A in there. But a daemon is basically a program that runs on a system and sort of hangs out in the background and waits for requests. And it does your bidding for you based on requests that you send to it. And so if we look at the Linux server, right, this is the process SSHD. The D switch probably tells it that it should be running as a daemon, because SSHD can do multiple things. And it's got manual pages, of course. But that program is basically running in the background, and its whole purpose for existing is to listen for connection requests. And so on my Linux laptop, when I say SSH, nick at Linux, blah, blah, it sends a message through the network to a particular place where this daemon is listening for requests. And when it sees that request, it goes through some kind of authentication, either asking for a username and password or doing some kind of handshake. And if it likes the authentication, then it goes ahead and it forks, and that fork becomes a new process, and that becomes a new process, and eventually it becomes bash. But this daemon continues to run in the background, right? It's got to continually listen for incoming connection requests. And so it can't be running bash and waiting for me to type in commands and sending me responses back. Because if it did that, other people wouldn't be able to connect, right? So this thing sits in the background, waits for connection request. If it finds a connection request, it makes a new process. That new process handles the whole interaction with whoever's connecting to it. And then when this shell exits, right, all of these things get shut down, but the daemon continues to run. And so that's probably the main thing that forks get used for in a Linux system, is just for creating processes. So this is the next piece of the picture. And I'm not holding you responsible for most of the details of any of this stuff, by the way, so you can relax and take it in. But I want you to see it because sometimes we write code and we're just writing code and it's running in a black box, right? But more and more that's not the case. More and more we're writing code that's part of an operating system or possibly bigger part of a cloud, right? So it's interacting with other processes, other systems, other users. And so understanding something about process hierarchies and creation and destruction is generally useful. So here's the next piece of the puzzle. So here's main, and we say fork. And we can look at the return value and we can identify whether we're a child or a parent. So there's another function call. It's called execl. And execl takes a file name and some other arguments, but primarily a file name. And it should be the name of an executable program. Okay, something that's been compiled and linked, something you could type from the bash command line and it would run. And what execl does is it opens up this file and it knows the structure of this file, so it looks inside and it figures out where the ones and zeros are that correspond to the program that was compiled. And it overwrites its own memory with those ones and zeros. In other words, it transforms itself into the program corresponding to this file name. So usually we do things in a pair, right? When we want to create a new process to run something like PS, for example, first we do a fork, which creates a parallel process. That parallel process self-identifies as the child, and then it makes a call to execl. It gives it a pointer to the program PS, and if everything's lined up correctly, the memory of this program, which is executing now, which is currently a clone of the original program, that memory gets overwritten. And it gets overwritten with the code from this file, which should be an executable program. And if you replace your memory with somebody else's memory, what happens? You become that other person, right? This is Blade Runner 101. So this process, which was a clone of the original main program, now becomes a program running PS, or whatever program we put into the argument for execl. And now we've got a truly separate process with its own identity, its own instructions, and ultimately its own set of variables and so on.
So the child always returns 0 for its status?
The child always returns 0 from fork. And the parent gets a return, which is the process ID of the child, which by convention is never 0. So if it's a non-zero return from fork, you know you're the parent.
What if
And
fork fails? What does it return then?
that's a good question. Probably, I don't know, maybe -1. So they usually put returns at the bottom of these manual pages. So let's just hop down there. Return values. On failure, -1 is returned in the parent. No child process is created. Okay. So if it's positive, then it's succeeded and you got the PID of the child. And the main reason fork will fail is because you run out of resources. That's probably I think that's the only thing that really bungles it up. All right, so let's look at execl. It's got multiple ways to call it. And you're running a program, so you want to be able to do things like pass command line arguments to this program. You want to be able to pass values of variables, right? So environment variables that you set up, like your prompt and your path and things like that. And so there's different versions of exec that let you pass different pieces of information in different formats. But execl is sort of the most basic. So let's play with that. So where were we? Not message of the day. Oh, I'm on the server. Okay, C4. All right, so we're going to do a fork, and the parent is just going to go to sleep for 100 seconds. Just because that's what parents do.
Just power naps in.
Yeah. Okay, otherwise, we're the child process. So we'll print a message. And let's change our identity. Well, let's do this first. And then we're going to modify it. All right, so we run bash, we execute C5, we've got two C5 processes running, right? This is the parent process, and it's got this weird thing that says HR time, which I'm assuming is related to sleep. This was the child process. 536 created a new process called shell, which was 537, created a process called PS, which was 538. Okay, so that's kind of what we did before. So let's see what happens if we do execl instead.
I think you have to close the quotes on the.
I do, thank you. Okay, and I am not 100% clear what these other arguments are, but I think they make it work. So the code is the command line arguments, and it seems to be okay with a null string, and then the null is for the environment variables. So we're going to do execl, and we're going to say /bin/ps. I forgot the dash L. I don't know if I can do dash L. I can't do dash L because I have to put my arguments in a separate variable, but we'll just fake it like this. Right. So the main thing is there's bash, that's our original process. Here's C5 that we're running. Here's the PS. We don't see another copy of C5, and we don't see a process running SH. Right? When we did this with, so let me get rid of the dash L here. When we do this with system, we got two C5s, we got a shell, and we got PS. When we do it with execl, we've got one C5 and one PS. And that's exactly what we should see.
So the PS is overriding the.
It's overwriting it. All right, this is what's happening when we call system. We say C5, C5 does a fork. We've got two C5s. The child process calls system, which creates a new process that runs SH, which creates a new process that runs PS. And so when we do our PS, we see all of those things. With this code where we're doing execl, we start off with bash, we run the program C5, we do our fork, we get another program C5, but then we say execl bin PS, and so we get this. That C5 basically morphs into a program running PS, a process running PS. And so when we look at PS, we just see those three processes.
Is that a security risk if you can't be sure exactly what you're running?
Sure. Yeah, so I mean, this is kind of like dynamite, right? We're replacing our program memory with whatever is in that file, right? And if it's malicious code, then we're going to be running malicious code, right? But it's really no different from typing that command at the bash prompt, right? Same thing's happening basically. But yeah, in general, you want to be cautious with that. And if it's not an executable program, right, it'll give you some sort of error message. So the man page for this is extensive, but return value -1 if an error occurs. So let's try the same thing. We're ready to call fork. We'll do the fork. The parent will go to sleep. The child will say, I'm the child. It'll do execl, save the return value in status, and then print out the value of status. And it works like we'd expect, except it never printed out the value of status. Is that disturbing?
Is it waiting for sleep?
Well, it got replaced.
It's not waiting for sleep. It can't print out the value of status because this code is not being executed anymore. Right? The child process completely overrode its program memory with the program stored in /bin/ps. So this never executes. Right? That's how you know that it's actually doing something. Whereas if we make a call to system and we save the return value and then we print that out, right, it tells us the return status from system was 0.
So execl will not return anything because it's basically a different program.
It's basically a different program, so that's this mysterious thing that it says down here. The exec function returns only if an error has occurred. Right? Because if no error occurs, then you change into something else. And you have no memory of what you were doing a moment earlier, which was to, return from execl and put the value into a variable. Right? That is no longer who you are. So you become a different program. And this, I think, is a fairly slick way to do process creation, right? Once you kind of get your brain around it, it's pretty straightforward to use this to create other processes that do things outside of what your own process did. right? And so this is what happens when you open up /bin/ps. You see all of this stuff, and it's 160,000 characters. And a lot of this is header, right? The elf in the beginning tells it that it's a compiled executable program. But somewhere in here are the actual binary instructions corresponding to whatever PS is supposed to do. And this is all just like text fields. But somewhere in there is the executable code that actually replaces your program memory when you call exec.
So everything before gets erased?
Basically, yeah, gets overwritten. Now, I don't know exactly what that means, though. So if your current thread is big and you use exec to run something very small, I don't know what happens to that extra memory that was there. I don't know if it's still available somewhere or if it somehow gets like zeroed out. I'm guessing it's probably still available. So this is the kind of stuff you look at when you're looking for exploits, right? This is fertile territory for where things can go wrong.
If you passed it null for variable, can you pass it multiple variables there? Like variable, comma, variable?
Yeah, so I'll confess I've never dug very far into the arguments. But this second argument is supposed to be your, I think it's your argv array, basically. And in this context, this third variable was null, but it could be an array of environment variables. So when you do this print environment, you get all of these things that are available to other programs, so your home directory and your type of terminal and your language and things like that. And you can make those available to a program. But you can pass like something like an argv array, and I think it's just an array of strings, and when you're done you have an empty string, and that marks the end of the array, and it'll figure out argc from there and so on. But really good exercise, if you want to play with this stuff, is to mess around with execl. Try to construct an argv array, and instead of running bin ps, run a C program of your own creation that basically just takes argc, argv, and prints them out and iterates through, and see if you can figure out what that second argument's doing. And when you look at argv, argc, right, if argc is 5, and you got 5 strings in argv, argv 0, 1, 2, 3, 4, argv bracket 5 is null. But remember, if you look at argv bracket 6, 7, 8, and so on, you start seeing these environment variables, right? So you could use a form of exec that also takes a array of environment variables and see if you can find those with a C program of your own creation. So there's lots of ways you can mess with this stuff, right? And this was what we did when I was in college, because all the stuff was closed source and there wasn't Google, so you just kind of like screw around with the stuff and take it apart and put it back together and see what happens. All right, 10 seconds, quick question. You should have an entry on Canvas asking you to do a teacher evaluation. Have you observed this? Okay, so how many people have done their evaluation? Cool, awesome, fantastic. If you haven't, please do that. It's really, really important.
Yes.
Okay.
You get extra credit for it?
It depends how you evaluate me. Of course.
You get 1 point if it's believable.
Yes, it's been suggested to give extra credit for that, but I'm not sure that that's actually doable. But you get better teachers if you do that evaluation and you do it honestly. So thank you for doing that. All right, cool. So I will see you tomorrow.
Like,